In this video, I will show you an RL parallel circuit example. For the following circuit, see, this is our given circuit. In this circuit, we are applying a sinusoidal voltage V equal to 28.28 sine omega t plus 53.13 degree, which is connected in parallel with a resistance of 3.33 ohm and with a inductive reactance of 2.5 ohm. So from this circuit we have to calculate the circuit admittance, total impedance, total current through the resistance R and the inductance L. We have to calculate the power factor, we have to calculate the active power, and finally we have to draw the current triangle or Phasor diagram and the admittance diagram or the admittance triangle of the circuit. So this is our given circuit. We are applying V equal to 28.28 sine omega t plus 53.13 degree. If I compare this applied voltage to standard sinusoidal voltage equation, V equal to Vm sine omega t plus initial phase of the applied voltage phi V, I will get Vm equal to 28.28 volt, and the initial phase of the applied voltage, which is phi V will be equal to 53.13 degree. Okay, now see the RMS voltage phasor. V vector will be equal to V phase angle phi V. This V will be equal to Vm over root 2 and phase angle phi V here equal to 53.13 degree. Now see, Vm is equal to 28.28. over root 2 with phase angle 53.13 degree. This will be equal to 53.13 degree volt. Okay, so this is our voltage phasor V. In this circuit, at first we have to find out the circuit admittance or total admittance YT. As this is a parallel RL circuit, the total admittance will be YR plus YL. Now see, in this branch the impedance is ZR, which is equal to 3.33 plus J0 ohm. Therefore the admittance of this branch, which is YR, and this is the reciprocal of ZR, 1 over ZR, that will be equal to 3.33 plus J0, 1 over 3.33 plus J0, which will be equal to 0.3 phase angle 0 degree Siemens. The impedance in this branch, which is ZL is equal to JXL or J 2.5 ohm. Therefore the admittance in this branch, which is YL will be equal to 1 over ZL or 1 over J 2.5 ohm, which is equal to minus J 0.4 Siemens. Okay, now see the total admittance in this circuit, which is YT will be equal to YR plus YL. Here this YR is equal to 0.3 and this YL is equal to minus J 0.4. Therefore the total admittance will be 0.3 minus J 0.4 Siemens. The total admittance YT is equal to 0.3 minus J 0.4 Siemens. Now see, after that we have to calculate the total impedance of the circuit. Now see, we know that the total impedance ZT is the reciprocal of the total admittance. So ZT will be equal to 1 over YT. Here YT is equal to 0.3 minus J 0.4. 1 over 0.3 minus J 0.4, which will be equal to 1.2 plus J 1.6 ohm. So in the circuit the total impedance is 1.2 plus J 1.6 ohm. After finding the total impedance Z, we have to calculate the total current I in the circuit. The total current I is the current that is flowing through this path. We have to find the current through the resistance R. Let's say I will denote that current with IR and this current with IL. So to calculate the total current, I will divide the total voltage V with the total impedance ZT. Total current is I, and that will be equal to total voltage V over total impedance Z or ZT. Here the total voltage is, see, 20, phase angle 53.13 degree, and the total impedance is 1.2 minus J 1.6 ohm. Or if I express impedance in polar form, I will get 2 phase angle minus 53.13 degree, and voltage is 20 phase angle 53.13 degree. So this I will be equal to 10 phase angle 0 degree ampere, when this 10 ampere will indicate the RMS value of total current. Now see, we have to calculate current through inductor, which is IL. IL will be equal to, as is a parallel circuit, the voltage across inductor is V and the impedance of the inductor or that branch is JXL. Therefore I can write it like this: 20 phase angle 53.13 degree and JXL will be 2.5 phase angle 90 degree in polar form. Okay, therefore IL will be equal to 8 phase angle minus 36.87 degree ampere, and the current through resistance is IR. The voltage across the resistance is V and the impedance of that branch is R with phase angle 0 degree. So here R is 3.33 and the voltage is 20 with phase angle 53.13 degree ampere. So IR will be equal to 6 with phase angle 53.13 degree ampere. After that we have to calculate the power factor and the active power. See, our RMS voltage V equal to 20 phase angle 53.13 degree volt, and RMS current I is equal to 10 phase angle 0 degree ampere. See here, initial phase of voltage, which is 5V, is equal to 53.13 degree, and initial phase of current or total current equal to 0 degree. Therefore the phase difference. Phi d is equal to phi v minus phi I, which is equal to 53.13 degree. Therefore the power factor, which is the cosine of phi d, will be cosine 53.13 degree, which is equal to 0.6. As this is RL circuit, that means this is an inductive circuit, therefore the power factor will be lagging. Okay, now see, we know the value of power factor, we know the RMS value of current, we know the RMS value of total voltage. Therefore the real power or active power P is equal to VI cosine phi d. Here VI is equal to 20 into 10 and cosine phi d is 0.6. So this will be 0.6 watt, or this will be equal to 120 watt. Or as we know the value of current that is flowing through the resistance, which is IR, we can use this formula. Real power or active power will be IR square into R. Here IR is equal to 6, so 6 square into 3.33. This will be approximately 120 watt. Now I will show you how to draw the current triangle or phasor diagram of this RL parallel circuit. At first we have to take a reference phasor. Usually we take that parameter as a reference phasor which remains same throughout the circuit. In the circuit, the voltage V equal to 20, phase angle 53.13 degree, volt remains same across the resistance R and inductance L. So reference phasor will be our voltage phasor. Okay, after drawing voltage V or after drawing the reference phasor, we will draw current phasor IR with respect to the reference phasor. Then we will draw current phasor IL with respect to the reference phasor V. Finally, we will use parallelogram method to draw the phasor diagram and current triangle. So at first we will take V equal to 20, phase angle 53.13 degree as reference phasor, as it is same across all the branches in the circuit. As the voltage V remains same across the resistance and inductance, we will take voltage V equal to 20 volt and phase angle 53.13 degree as our reference phasor. Let's say this is our positive x-axis. The reference phasor has a voltage of 20 volt. It will create an angle of 53.13 degree with respect to plus x-axis. Okay, now see, the current IR is the current that is going through the resistance. If I have a resistance R, if the current through the resistance is IR and the voltage across the resistance is VR, in case of resistor, the voltage V and the current I will go in the same direction, so VR and IR will be in phase. So similar case is applicable in case of this circuit. In the circuit, the voltage across the resistance is V and the current is IR. See here, the current IR will have a magnitude of 6 and it will create 53.13 degree angle with respect to this plus x-axis. That means the voltage V and IR will go in same direction. Let's say this line is our current IR, which has a magnitude of 6 ampere and it is creating 53.13 degree with respect to this plus x-axis. After that we will draw the inductor current with respect to this V. In case of an inductor, if the current through the inductor is IL and the voltage across the inductor is VL, you will see the voltage across the inductor VL will lead the current through the inductor by an angle of 90 degree. Here the voltage across the inductor is V and the current is IL. Therefore you will see, as V is going in this direction, IL will create 90 degree with respect to this V. Let's say, see, this IL has a magnitude of 8 ampere and it will create an angle of minus 36.87 degree with respect to plus x axis. See, if I have plus x axis, if I move in the counterclockwise direction, the created angle theta will be positive. If I go in the clockwise direction, the created angle theta will be negative. So to create minus 36.87 degree, we will move in clockwise direction, and let's say this line is indicating our IL equal to 8 ampere and it is creating minus 36.87 degree. And you will see the overall angle, the angle between the voltage across the inductor and the current through the inductor is 90 degree, 53.13 plus 36.87 degree. Okay, now see, I can draw an equal vector from this point, and that equal vector will be in parallel with this IR. Let's say this is that equal vector. That means equal vector, that means they will go in the same direction and the magnitude will be same and they will be in parallel. Let's see, I can draw an equal vector from this point, and that equal vector will be the IL vector. IL vector, that means it will have the same magnitude as the current IL and it will be in parallel with this IL, or this equal vector will go in the same direction as this IL. Now see, we have this IR and this IL. If I add IR and IL, I will get the total current I. So let's say if I add IR and IL, I will get the total current I here. Let's say this will be O, this will be A, this will be B, and this will be C. You will see this O, A, B, C will make a parallelogram. We used the equal vector to draw the parallelogram. If you want to see the neat sketch of the Phasor diagram, I will get a figure like this. This black line will indicate the voltage phasor whose magnitude will be 20 volt. This red line will indicate IR phasor whose magnitude will be 6 ampere, and I will denote that with OA. This green line will indicate OC, or IL current phasor whose magnitude will be 8 ampere. This will create minus 36.87 degree. And if I want to draw an equal vector of this OA, I can draw it like this. From this point to this point, I will get CB. CB is exactly equal to OA. Okay, and I can draw an equal vector from this point, and that will be AB. The equal vector will be AB, and AB will be exactly equal to OC. That will be our current phasor IL, and this will be our current phasor IR. Okay, now see, if we look at OAB triangle, that will be a right triangle because this angle is 90 degree. OA is our current phasor IR. AB is our current phasor IL. Now see, if I go directly from this O to this B, OB vector will be the sum of OA and AB. This OB will indicate the total current I. This OA is current through the resistor IR. This AB is the current through the inductor IL. Therefore, you will see I is equal to IR plus IL. See, we are using this OAB right triangle using the current IR, IL and I. Therefore, this OAB will indicate a current triangle. Now look at the triangle OCB, as this is the opposite angle of this angle, so this will be 90 degree. So this will be a right triangle. In this right triangle, this OC is our inductive current phasor IL. This CB is the current phasor IR. If I go directly from O to B, OB will indicate the vector sum of OC and CB. Here this OB is the total current I, OC is the IL and CB is the IR. So you will see I can draw this right triangle using currents IL, IR and I. Therefore, this OCB will create another current triangle. And this overall diagram is known as the phasor diagram. Of the given parallel RL circuit. Now I will show you how to draw the admittance diagram or admittance triangle of RL circuit. See, previously I deduced y equal to 0.3 minus j 0.4. In polar form, that will be equal to 0.5 phase angle minus 53.13 degree Siemens. Now see, to draw the admittance diagram, at first we have to take real and imaginary axis. We take the real axis in the direction of plus x. We take the imaginary axis in the direction of y. This will indicate plus j and this will indicate minus j. Now see, y is equal to 0.3 minus j 0.4. If I compare this equation with standard G minus JBL form, you will see here the conductance G will be equal to 0.3 with phase angle 0 degree Siemens, and minus JBL will be equal to minus J 0.4 or 0.4 with phase angle minus 90 degree Siemens. Okay, that means this 0.4 or this BL will create minus 90 degree angle with this real axis. So let's say I am taking G in this direction. That will be OA. That will be our G, 0.3 phase angle 0 degree. Okay, this is our G, and we will take minus JBL in this direction. Minus JBL is equal to 0.4 phase angle minus 90 degree. That means it will create minus 90 degree angle with this real axis. As we are moving in the clockwise direction, the angle will be minus 90 degree. Okay, so this will be OC, let's say. Now see, this OA is the conductance G. I can draw an equal vector of this OA from this point. Let's say this CB will be the equal vector of this OA. I can draw another equal vector from this point. Let's say that will be AB. AB will be equal vector of OC equal to minus JBL. See, if I add G and minus JBL, that means if I add OA and AB, that means G minus JBL, I will get OB or admittance Y. Okay, so this will be our admittance. Admittance Y will create how much angle? Minus 53.13 degree. Minus 53.13 degree with the real axis. Okay, so this will be the admittance diagram. See, this is our neat sketch. You will see this angle will be 90 degree. So this angle will be 90 degree as we have drawn parallelogram. Using the equal vectors. So this OABC is a parallelogram, and in this parallelogram you will see OAB will be an admittance triangle, and this OCB will another admittance triangle, where this OA is indicating G, this AB is indicating minus JBL, and OB is indicating the total admittance Y. In case of this OCB, you will see this OC will indicate minus JBL, CB will indicate G, and OB will indicate Y. Okay, that's it. Thank you.